Hello, in this video we're going to do a few more examples of limits of sequences. So here we have 6 examples that I'd like you to work out on your own and come back and check your work following that on the rest of this video. So the first one is the terms of the sequence are a sub k equals natural logarithm of 1 plus k squared divided by the natural logarithm of 4 plus 3k. And the next one, b sub k equals k squared over e to the k power. The next one is a sub k equals a fraction. The numerator is k factorial. The denominator is 4k minus 3 in parentheses times k minus 1 factorial. The next one is e to the negative 2k power times sine cubed of 2k. The next one is c sub k is square root of k squared plus 1 minus k. And the last one is k squared times 3 to the k power times sine of k over 5 to the k power. Now use what we just talked about in terms of function dominance to give you some idea about what the limit is ahead of time. See if you can figure out what you think it might be. And then go ahead and work out the details with whatever techniques you might need to use. You might need to use L'Hopital's rule, you might need to use a squeeze theorem, you might need to use some other algebraic techniques. Okay, work on these your own and come back when you're done. Press pause now. All right, here's the first one. If we look at this, these top and bottom are both logarithms, so we would not be surprised to see a constant limit. When we take the limit as k goes to infinity of the top and bottom separately, they both go to infinity. So this tells us we can use L'Hopital's rule. To do that, we switch to variable x, and by that we mean that we are actually thinking of these as continuous, in fact, differentiable functions in the numerator and denominator. Now we can take the derivative of the top and bottom separately and do that ratio, and we get the limit of that should be the limit of the same one here, provided these limits exist. The derivative of log of u is 1 over u times the derivative of u, so this is 1 over 1 plus x squared. The derivative of 1 plus x squared is 2x, so that's 2x over 1 plus x squared for the numerator. The derivative in the bottom is similarly 1 over 4 plus 3x times the derivative of the inside, which is just 3. Now, just inverting and multiplying, or if you want to think of it as multiplying the top and bottom by both of these little denominators, we end up with 2x times 4 plus 3x over 3 times 1 plus x squared. This multiplies out to be 6x squared plus 8x in the numerator and 3x squared plus 3 in the denominator, and that used the distributive property. Now, we should know that we have a rational function like this. When they're the same degree, we're going to get the ratio of the first coefficients in the leading coefficients, that is, in the numerator denominator, so it'd be 6/3 or 2. One way we can see that is multiply top and bottom by 1 over x squared and distribute, which gives us this. Then our property of limits says these, we can bring the limits inside here, and the limit of both of these little fractions is 0, so we get 6/3 or 2. For b, we've got an exponential in the bottom and a k squared, or just a polynomial, in the top, and that will dominate in the bottom. So this should they both go to infinity, but the bottom goes to infinity faster. So we should get 0 here. We use L'Hopital's rule to verify this. We'll use it twice. So again, switch to x's. Take the derivative of the top and bottom. We get 2x over e to the x. Then you're still going to inform infinity over infinity. It was up here. It is again here. Use L'Hopital's rule again. That's 2 in the top for the derivative and e to the x in the bottom. Now the bottom goes to infinity, the top stays at 2. That means that the limit's going to 0. Now in this one, we do some canceling here. K factorial is k times k minus 1 factorial. And these k minus 1 factorials have the same factor, so they cancel out here. Everything is factored. So remember that k minus 1 is factorial is k minus 1 times k minus 2 times k minus 3 down to 5, 4, 3, 2, 1. Works us all the way down to 1. And so does this right here. So all of those k minus 1 factors from 1, 2, 3 up to k minus 1 are included in that factorial, both in the top and bottom. They cancel. Well, that just leaves a rational function, and we're going to get the ratio of the coefficients 1 over 4 for the answer. One way to see that is multiply top and bottom by 1 over k, and the derivative of this part is 0, and so you get 1/4. Or we could use L'Hopital's rule once again by switching to x's and do a derivative. Either way, we get 1/4. Here, here we have this one right here. The exponential is going to go to 0. The sign is just going to, well, it's going to vary somewhere at least between -1 and 1. And so that exponential is going to dominate, forcing this thing down to 0. We can verify this with the squeeze theorem. Sine of 2k, sine of anything is going to be between -1 and 1. So when we cube this, you cube all three parts. -1 cubed is -1, 1 cubed is 1. Middle we get sine cubed. That's going to still be same relationship there. And then we take then the limit of all three pieces. We still have the same inequalities going across, but the ones on both ends are 0. And so the squeeze theorem tells us the limit in the middle must be 0 as well. And I don't have the e to the k there, so this should be e to the minus 2k should have been right there. There we go. Let's go ahead and just do this here. Okay, that's a little better, showing all the steps. And so anyway, we get a limit of 0. The next one, we have both of these parts approach infinity, but it should be about the same rate. The square root of k squared is k. So there's a good chance this difference could be 0, or it might be some other real number, but we'd expect maybe a limit here. So we don't necessarily expect it to go to infinity, but let's take a look and see what happens. We multiply the top and bottom by the conjugate. Infinity minus infinity is an indeterminate form, but we can't use L'Hopital's rule. This one here, we multiply by this conjugate, and so we get a minus b times a plus b in the top. Of course, we have to multiply the bottom by the same thing to make this equals valid. And then in the top, you get a squared minus b squared. So that's the square, and the square root cancel leaves you k squared plus 1 minus the square of the k. And then the k squares cancel, leaving you 1 at the top. And now with a plus here, as all of this in the bottom is going to infinity, so this has the form of constant over infinity, we know that's going to 0. So this one we had here was what we're looking at for this limit. Turns out to be 0. So at the moment we're going to ignore the sign of k. 3 to the k over 5k is 3/5 to the k, which is a geometric sequence, exponential function, that is going to converge to 0. It's going to dominate over the k square. Multiplying by the sign is not going to change that. It's going to force the whole thing down to 0. Working the details out involves a few things. First of all, rewrite this as k squared over 5/3 to the k, leaving out the sign term. Switch to x's. So what that like thing of is continuous, fact differentiable functions in the top and bottom. So we can take the derivative of the top and bottom using L'Hopital's rule. The top and the bottom both go to infinity. So the derivative of the top is 2x. Derivative of the bottom is, well, b to the x is natural log of b times b to the x is the derivative. And we're still in the form infinity over infinity, so do another derivative of the top and bottom, applying L'Hopital's rule a second time. The derivative of the top is 2. The derivative of the bottom, again, is the natural log of 5/3 times 5/3 to the x times the other natural log of 5/3 that we had at the beginning. So it's natural log of 5/3 squared times 5/3 to the x. Now, the top is fixed, but the bottom's going to infinity still, so that whole fraction goes to 0. Sine of k is between -1 and 1, so when you multiply by this original expression here on all three sides of this, we get our thing that we're looking for in the middle, sandwiched between these two things. Take the limit as everything goes to infinity, and the ones on the ends, we just proved that that goes to 0, so its opposite is also going to go to 0. And so the squeeze theorem, this thing gets squeezed in the middle to have a limit of 0, so that verifies that. So hopefully now it's time you can give you that gives you a little more help maybe on some of the homework problems where you might have to do a lot of these limits of sequences.